Modern professionals routinely transmit highly sensitive data across the internet. Whether it's a signed legal contract, a corporate tax return, or a raw API key, we rely heavily on central cloud platforms to move these files from point A to point B. To protect this data, the industry standard is a security model known as encryption at rest. Most major cloud providers heavily market this feature as the ultimate safeguard for your files. The mechanics of encryption at rest are straightforward. You upload your data in plain text. Once that data arrives at the provider's database, their servers apply the encryption before writing it to a hard drive. This diagram illustrates the critical architectural vulnerability in that standard model. The cloud provider generates the decryption keys on their own hardware, and they hold those keys indefinitely alongside your locked files. This creates a system of policy-based trust. The privacy of your data relies entirely on the provider's legal promise not to look. As the text here shows, if the provider is compelled by a warrant, or if they suffer an internal data breach, that legal promise is easily broken. Because standard cloud hosts retain the master keys, labeling the data as encrypted does not mean it is actually private from the host itself. This presents an engineering challenge. How do we design a system that routes a file through a central cloud server while making it mathematically impossible for that server to read the data? We need a truly blind transfer. The definitive answer to this challenge is a zero-knowledge architecture. Returning to our diagram, we can contrast the flawed standard model directly with the zero-knowledge approach. Here, on the right side, the user retains the only decryption key, keeping it entirely separate from the server infrastructure. In a true zero-knowledge system, the central server is demoted. It acts purely as blind storage, holding only scrambled, unreadable chunks of data. As highlighted here, this structural shift moves data security away from a fragile legal policy. It turns privacy into an unbreakable mathematical certainty. By strictly engineering the exclusion of the decryption key from the server's possession, we completely eliminate the need to trust the cloud provider. Building a blind server requires shifting the actual encryption boundary away from the cloud. The encryption must happen directly on the user's local device before the upload phase even begins. This schematic shows local encryption using the browser's native Web Crypto API. It utilizes the AES 256 GCM standard to scramble and verify data within isolated memory. The encrypted file is then divided into smaller chunks for network transit. Only after this localized scrambling is complete do these encrypted chunks leave the local machine and get pushed over the network to the central server. When the central server receives the upload, it successfully hosts the data, but it utterly lacks the means to interpret the information it is holding. It is the digital equivalent of filling a physical lockbox and scrambling the combination dial before you ever carry it out of your front door. Enforcing client-side execution ensures the cloud provider never possesses the plain text data at any single point in the transfer lifecycle. This brings us to the next major architectural problem. If the server doesn't possess the key, how does the sender seamlessly transmit that exact key to the recipient? The obvious instinct might be to simply bundle the key alongside the encrypted payload during the upload, but doing so would immediately compromise the blind server by handing it the key. The protocol solves this by decoupling the key from the payload, exploiting a strict rule of web browser routing using the URL hash fragment. This fragment is the portion of a web address following the pound symbol. Mechanically, all web browsers follow a uniform behavior. Any text placed after a hash symbol in a URL is processed strictly on the local machine. When a browser requests a web page, it deliberately strips off the entire hash fragment before sending the request across the internet. The zero-knowledge protocol utilizes this quirk, appending the decryption key as that hash fragment, anchoring it locally. The final sharing link you send to a recipient is actually a hybrid. It contains a server routing address for the encrypted payload and a purely local decryption key tacked onto the end. By embedding the key in the hash fragment, the protocol weaponizes the URL into a secure, decentralized delivery vehicle that the server can never intercept. While the server is blind, sending the complete URL, both the link and the hash key, over a single unencrypted channel like email still presents an interception vulnerability. If a malicious actor compromises the recipient's email inbox, they suddenly possess both the encrypted payload address and the decryption key simultaneously. This diagram maps out splitting the channel, separating the payload location from the key. Step 1 transmits strictly the base URL via email. Step 2 transmits the extracted hash key via a secondary encrypted channel like Signal. Under this setup, an attacker intercepting the email payload only finds a link. That link points to mathematically locked, useless data without the corresponding out-of-band key. Channel splitting ensures that a catastrophic breach in standard communication protocols cannot compromise the core integrity of the zero-knowledge transfer. The golden rule of modern cryptography is simple. Proprietary, closed-source security protocols cannot and should not be trusted. A true zero-knowledge system must allow users to independently audit the underlying code. The source must be open so researchers can prove the server is actually blind. This checklist confirms the protocol's auditable architecture. By relying on standard vanilla JS on the front end and a deterministic Python backend, the entire pipeline is easily reviewed by security professionals. Beyond the source code, we have to look at operational transparency. We need to know exactly what metadata the server actually logs during a live file transfer. This transparency receipt details the metadata the server retains. As shown left, it logs routing data like IP hash and file size. Contrast this immediately with the right. File names, content, and the decryption key are mathematically excluded. Robust encryption is only one pillar of privacy. A secure system must also provide absolute proof that the server remains exactly as blind as it claims to be. Historically, maximum data security demanded maximum user friction. Protecting a file usually meant requiring specialized software, managing complex key exchanges, and training users on difficult workflows. Leveraging native browser architecture bypasses this friction entirely. It removes the need for user accounts, logins, or application installations for both the sender and the recipient. The user's standard web browser acts simultaneously as the local lock, the key generator, and the secure transmission vehicle. We are turning an everyday web browser into a military-grade, zero-knowledge transfer node, all without changing existing user habits. By combining client-side AES encryption with the mechanical quirks of URL hash fragments, we achieve a mathematically guaranteed privacy model that requires zero trust in the network itself.